Okay, let's continue. Actually, the objective of this chapter is to find the relationship between moment here and the sigma xx tau xy. So, for example, we have a bending moment. And then we have bending moment. And we will find the bending moment relationship with the sigma x. And then the sigma x is a function of y. Yeah, so between equilibrium equation. So we can find from equilibrium equation and find the distribution of stress of sigma. So this is our major objective in this chapter. And okay, so we start to. This is a little bit difficult derive, but please maybe understand at your best. Okay, we start. Let's start. We need to, yes, we need to start from here. For example, this is a bin, and is a subject by a external load P. And let's start to find the relationship of the equilibrium equation. And do your best to know in detail, to know what I'm saying. This is a bin, and this is external load. So we call this is a deformation. It's like a curve. So curve. This is the center of curve. And the rho QB is the radius of curve. Maybe long distance. This is a long distance. Okay. and we start from the. We need to define some special character. It's a rho equal is a radius of curvature. Because it is a curve. And we also need to define the kappa. This is a kappa. We call kappa. The kappa is equal to 1 divided by rho. This is just a definition. That means it's a reciprocal. So this is a definition. So the radius the reciprocal of the radius we call kappa as curvature. So we say kappa is a kind of curvature. Okay. And now, according to the formulation of circle formulation, and we can get the small distance ds is equal to rho d theta. D theta is here. D theta is a small angle. D theta is a small angle, and the ds is on the curve is a small length, and a small theta, and the radius. So according to the circular formulation, we can get this is the distance, this is the curve, the length is equal to the radius to multiple the angle. So we get ES equal to rho d theta. So this is a mathematics. This is a formulation of circulus of a circle. Therefore, the kappa is equal to the reciprocal of radius of curvature is equal to d theta divided by ES. And if the deformation is small, that means if the deformation is small, most of the time it's small. Most of the time it is small. So we will get the ds almost equal to dx. These two values is almost the same. It's almost the same. So last we can get the kappa is equal to d theta divided dx. This is a very important result now, because kappa is equal to d theta dx, and also equal to reciprocal of radius curvature. Yeah, so please, until now, this is our very important result until now. Okay, so let's continue. If you have this kind of understanding, and we can continue to this diagram. You can look the picture on the right hand side. If we call the length of, and in this time, please be careful about this. We want to talk more in detail. There is a line here. The dotted line we call is the on the axis. This is a special name in this analysis. We call it a neutral line. Neutral axis. And also on the plane is a neutral plane. Because here is a shortening. Here is extension. But in here is a no extension, no shortening. So we call, in this case, the no strain. Keep the original length. So the strain is equal to 0. Strain, normal strain. Is 0 in this plane. So we call neutral plane. Neutral plane is a very, very important idea here. Okay. So please remember, this is the very, very important idea for the analysis. So let's go for. So in this case, we have a definition of this. This is actually this axis is, what is this axis? If you know, this is yes. And we need to define this the length. If L1 is the length of EF. So here is L1. If we define, this is L1. So L1 is the length after bending. In this case, we know it's a shortening. Yeah. So should be L1 is equal to rho minus y and d theta. Why? You will look, this is the center. Yeah, this is the center. So this is the center. So the distance here is rho, and this is the, yes, we will define the y. The definition of y is the distance from neutral axis. So the y, the definition of y is the distance from the neutral axis. So that is the length. The length here should be equal to rho minus y. Rho minus y is the length. So the rho minus y, this is a rho. From here to here is rho, and the minus distance y. So the y is here. Y here. Y is here. So the rho minus y is the distance here. So the distance here and the multiple d theta. So it's equal to the EF L1. So L1 is equal to rho minus y in the multiple d theta. And according to this equation, yeah. According to this equation, and we can get, because now dx d theta is equal to rho dx. The theta is equal to dx minus rho. So you can get is a dx minus y and then rho dx. Yeah. So we can get the relationship of this. And we keep going. Please know in detail. No, do your best. Okay. Now, what is epsilon x? What is epsilon x? Is the normal strain. At the position Y. Yeah, so epsilon x, actually epsilon x is a deformation, is a strain. So this is the original strain. This is the after deformation and the minus dx, because this is the original. And this is the after deformation, after deformed. Yeah, after deformed. After deformed. So the strain is the difference of length. So the strain is equal to L1 minus dx. This is we call the strain. So, and then you can get the epsilon x is equal to minus y divided by rho, and equal to minus kappa y. So this is the very important result of this section. We can get the epsilon x is equal to kappa and multiplied by y. Yeah. So please remember this relationship.